Peter Wadhams is off. He told me he was going to Greenland, but I thought he'd be back. He said he would, but you guys can hold your own, I'm sure. I don't know who's going to be on which
Peter
side.
Wadhams is off. He told me.
All right, we're live now, and I'm going to introduce you in 1 minute. Hi, I'm Metta Spencer. I'm in Toronto, but we are going to have some little bit of traveling today. Main thing of the interest today is that we got to save the world. And, you know, it's getting more difficult every day. This operation that I've been engaged in for the last couple of years is called Project Save the World. And this is one where we actually get close to some of the real challenges, because, you know, there have been extinction events before when practically everything living on the planet was wiped out. And I've got some experts with me today who are very familiar with those concerns about the conditions that led to those exterminations or extinctions, and whether or not we are getting close to repeating this situation. So if you want to be scared, just hang on, and somebody is going to curl your hair today with predictions or maybe reassurances. I don't know. Maybe a little of both. I have basically 3 guests at the moment. There may be a 4th one showing up, who's maybe delayed. In Ottawa, here's Paul Beckwith, who's a climatologist, and he has his own series of videos. He puts out a lot more than I do sometimes, I think, and at least they're pretty smart videos about climate change. So good morning, Paul. How are you?
I'm good, thank you.
Good. Peter Wadhams is not here, but I hope he will be able to join us. Near Seattle, I believe, Peter Ward is at his desk. Hello, Peter.
Hello, and thank you for having us all.
It's wonderful to talk to you and to introduce you all to each other, because you're probably the biggest extinction event expert around, and other things that are connected to that threat are in the orbit and the bailiwick of the other speakers. So we will have a conversation about things that you're very familiar with. Now, I believe you're near Philadelphia, or no, where are you, Paul? Where? But you told me 10 times and I never remember. Where are you, Paul?
I'm in a place that was supposed to be part of the capital of the United States until Virginia took it back.
Okay, so
I'm in a place called Arlington, Virginia.
Okay.
And might mention that I started out for a year working in the Senate office that was evaluating climate legislation.
Mm-hmm.
And that was the great year of climate bills in the Congress. And I was the only serious scientist in the group evaluating them. And that's when I saw the work of Peter Ward. Okay. And that's when I learned that Peter is one of the 4 top experts in the world on past mass extinctions of life on the earth. I am very grateful to have met Peter.
Well, here's Peter Wadhams. Good. Now the gang's all here. Good. Hello, Peter. How are you? You're muted, so unmute yourself and join the gang. I have introduced everybody else, and now I will have an opportunity to introduce you, because I thought you might still be in Greenland. You said you were going to be off looking at some sea ice, right? Well, so this is Peter Wadhams, and you're in Italy, I believe. Are you back in Italy? And Peter Wadhams is a leading expert on sea ice. So I think today what we need, I have a lot of questions that have arisen in my mind as a result of listening to you 4 guys over the last several sessions. And maybe you can help me get clarity, but mostly talk to each other, because I don't know whether you all agree about everything. I think you're all worried about the change of the currents in the ocean. So we need to talk about that. I know that you are worried about the changing salinity and temperature of the ocean. I think you're talking, I've heard you talk about things like the stratification of oceans. I've heard you talk about things like the possibility that phytoplankton could either be really wonderful for us. I've heard Paul Beckwith say that we need to sprinkle iron in the ocean to increase the phytoplanktons, because that's going to take the CO2 out of the atmosphere to the bottom of the ocean and sequester it. And then I've heard Peter and Paul in a different show, Peter Ward and Paul Werbos, talking about how if the phytoplanktons go to the bottom of the ocean, they're going to decay and feed the microbes that produce hydrogen sulfide, and that's going to do us in. So I want to know whether I should like algae or not, and whether these stories can be made to coincide and be compatible or not. So we've got to figure out what we have to do to save the world from these catastrophes. And I don't know where to begin. So I think maybe, shall I ask Peter Ward to begin? Because you're the biggest expert on extinctions, all right? Give us your vision of the situation and the challenge and what this has to do with ocean currents and ocean stratification. Give us a scenario for doomsday.
Well, I don't want to be doomsday or REM is the end of the world as we know it, and I feel fine. Actually, I don't feel fine at all. I'm living in Seattle, Washington, where none of us have air conditioning, and we just had a huge heat event since the last time I've talked to you, Meta. We had another one last week. When it hits 100 degrees Fahrenheit in Seattle, Washington, people suffer, and we have, as in British Columbia, had many, many deaths now attributed to heat. And overheating is really a killer of humans. If you want to think about overheating, though, the overheating is really telling us that from a species point of view, times of really intense global warming have been the times of mass extinction. And they all coincide with rapid rises of carbon dioxide. Now, the two that really come to mind are really, there's one at about 60 million years ago at the end of the Paleocene period, the Paleocene-Eocene transition, where temperatures spiked enormously. And this was because of a release of methane from high latitudes. But the other really bad one was way back at the end of the Permian, 252 million years ago. And both of them seem to be associated with a change in ocean currents. And the reason that's relevant now, as we saw in the news this past 2 weeks, and your really distinguished people here with me can speak to this much better than I, but one of the currents most important for maintaining climate, at least in the equilibrium we've had for the last 10,000 years, emanates in the North Atlantic. It goes to the Gulf Stream, it moves up north, and then it sinks. This is a conveyor belt current. It's not just on the surface. It moves on the surface, goes down deep, and comes back on the bottom. Those types of currents have been important for stability, climate stability. At the end of the Permian, that type of current stopped. At the end of the Paleocene, that type of current stopped. And two things happened. We had a lack of oxygen on the deep ocean, which led to a lot of really nasty critters producing hydrogen sulfide down there. And we had ultimately something called the rise of the chemocline, where you have a lot of this really bad, low oxygen, zero oxygen bottom water rising to the surface, causing death in the surface waters. So when I hear that this North Atlantic current is itself apparently slowing, and again, your experts are going to know much more than I, this has to be, at least for a paleontologist such as me, a huge red blinking, screaming, watch out world type of warning. And I think I'll end there.
Okay, good. Well, who wants to pick up from that?
Well, I could carry on about the current because I mean, it is recently attracted a lot of attention. There have been papers published on it, or a paper, which I think is sort of misleading. But you're right in saying if this current is slowing or stopping, it will have ghastly consequences or nasty consequences similar to the ones that happened in these earlier periods. And the thing that has been going on is, which we've been studying since the 1990s, and has been that the conveyor belt current that we're talking about, the Atlantic thermal halide circulation, had all conveyor belts have an important place where they sink. Otherwise, they don't remain. The water doesn't remain where it starts. So the conveyor belt in the North Atlantic, the big sinking area, was a very, very small region in the Greenland Sea at 75 north and 0 west, right in the middle of the cold part of the Greenland Sea. And it was discovered that, well, partly by us, but that if you, in that region, very, very small region, you get intense sinking because of the increase of the density of the water caused by the fact that the sea ice is growing very rapidly there, or was. And that was giving you intense, very, very, very dense water, which was sinking. And that was producing something like water going down a plug hole, a rotating column of water sinking down. And you were finding that surface water was sinking to 3,000 meters below the surface without any change of properties. So it was a uniform water mass going from the surface to 3,000 meters, which is very, very rare. And what was even more rare was that it was staying like that for years. We tracked these, they're called chimneys, and we tracked them for 3 years, and they would stop chimneying during the summer when there was meltwater on the surface. Then they come back again and sink away for another, all through the winter. So it was an extraordinary phenomenon, and not really seen anywhere else in the ocean, and very, very a very, very serious process. The trouble is, it then stopped suddenly in just about 2005, 2006. Suddenly it stopped, and it stopped basically because sea ice stopped forming in the Greenland Sea because of global warming. So you're not getting any sea ice forming, so you're not getting any opportunity to make the water more dense from the ice that's formed. And so that whole chimney world stopped. And
Can I ask about it, Peter? Because now we'll get clear. Now we're talking about the currents, a single system of currents that goes all around the world, this thermohaline current. But now there's something called the Gulf Stream. Is the Gulf Stream just one segment of that thermohaline current, or is it something different? And is this, you're talking about like a conveyor belt, it goes up to the Greenland Sea and then it goes down a chimney and it comes back?
No, I might be able to help a little on this. I might be able to help a little.
Okay.
There's not one thermohaline current in the world. So thermohaline current refers to a convection current caused by these variations in density, which are related to the temperature and saltiness of the water. There are two very important thermohaline currents. Anybody who makes policy connected to climate really needs to understand at least the two most important thermohaline currents on our planet. One of them is the one that's behind Paul Beckwith's head, the Arctic North Atlantic current, where the Gulf Stream is the center of that. But then there's another current, and I happen to have a slide on it, of what comes out of the Antarctic, something called the Humboldt current, which is what powers the oxygen of the Pacific Ocean. And right now, the Gulf Stream looks very big to us. If you live in Europe, if the Gulf Stream freezes over, England freezes over, you got a lot of problems very soon in Europe. These are urgent, serious, the military is worried about them. But the current in the Antarctic, feeding oxygen to the Pacific, that's the current responsible for the big mass extinction that Peter was talking about. the gigantic Permian Triassic extinction, there's a lot of room in the Pacific, and you can grow a lot of bad bugs. I wouldn't call them phytoplankton. I call them archaea, but these guys produce H2S and they can kill everybody on Earth. So we have a short-term problem in the next decade or two with the Gulf Stream conking out and freezing people. But we got this other current, the Humboldt, where the warming is blocking those same chimneys. They got chimneys at the South Pole too, not only the North Pole. And those chimneys at the South Pole, they call them Paulinias. If they get blocked, we're all dead.
Okay, so these two currents, the Humboldt and the North Atlantic current, are not connected. I saw a map that made it look like there was one big loop all around the Pacific and the Atlantic. If you waited a few thousand years, you'd see the whole thing happen, move it from one place to another. But they're not connected. Those are separate currents. Is that right?
They're all part of the same global ocean circulation pattern. So they are connected, but it's a long range connection. But the water, is cycling around the planet. I mean, the equator is warm, the poles are cold. Heat wants to travel from the equator to the poles. It does so in the ocean current and also in the atmosphere, and results in, it's the reason why the jet stream exists. Now, as far as a sure sign that the Gulf Stream coming up here is slowing is in this region here, south of Greenland, there's a persistent cold area. It's called the global warming hole. Some people use that expression because it's not warming in this region. And the main reason, I think, is that the Gulf Stream has slowed down and is shifted. So it's not bringing all this heat up to that region. So it's anomalously cold there. People first thought it was just melt water from Greenland that was cooling that region, but it appears to be more of an ocean circulation issue. So yeah, there was a lot of noise about the Gulf Stream slowing down about a decade or so, 10, 15 years ago. But there were some papers subsequent to that said that there's a high variability in the current flow rates of the Gulf Stream. And, maybe it wasn't slowing down that 15% or so, but further studies, and more recent studies have shown, yes, the trends are definitely down. I mean, they have a lot of ocean buoys at, I think, 26.5 degrees north or so, where they have the Argo floats, which are at the surface and they descend through the water column thousands of meters, recording temperature and salinity and oxygen levels and all these things. So we have lots of good data on how the ocean is changing, and it's definitely, hot water is lighter, it floats on top of the surface, so we're getting more stratification of the oceans, we're getting less vertical mixing, and this is a huge problem because you get these dead zones, if you like, in more and more regions of the ocean. Mostly it's on shallow continental shelves, where you get phytoplankton blooms and then they sink down and the microbes eat them and it uses up all the oxygen near the bottom. You get these massive dead zones. But in the open ocean, it's quite different. I mean, there's not that much oxygen at the bottom of the ocean to begin with. So, and whenever there's a big source of dust, of course, is from the deserts in Africa. The Sahara, the winds blow the dust and that deposits iron in the ocean, and the iron stimulates phytoplankton blooms. So, I think, so it's an interesting question, you were saying, does phytoplankton help or does it harm, right? And, we have seen drops of phytoplankton levels over the last decades, but the drops aren't as much as we originally thought, because actually the appearance of the phytoplankton from satellites was changing. So the color of some of the phytoplankton was changing. So there were still lots there, but we didn't think they were there because they were changing physical structure and things. And also the acidification of the ocean is a huge problem, because the phytoplankton and other marine creatures they have calcium carbonate shells, aragonite and calcite shells, and those shells can't form when the water is too acidic. So there's all of these issues coming at us fast and furious.
Can I ask one, when you talk about it stratified, it's getting more stratified because the current is slowing. Is that the idea? There's a connection between those two phenomena or no?
Well, you could talk about ocean mixing from the chimneys, which is a huge source of deep water. Like it takes water from the surface and it carries it deep down, and that water, because it's from the surface, is well oxygenated, and the water that upwells other places brings up nutrients to the surface. So you can talk about, but if the ocean is warmer, that warm water, wants to stay on the surface, and there's less mixing with the cooler water from below. So if there's less vertical mixing, this is widespread over the oceans. I'm not talking about just a specific chimney area. Then there's less oxygen going down, going deeper. There's less CO2. The gases that are dissolved in the seawater aren't being carried to deeper levels because there's less vertical motion, vertical mixing.
Okay, now, Peter Ward, my guess is that what worries you is that if the bottom of the ocean doesn't have enough oxygen, is that the problem?
Yes.
That's what you mean by stratified. What is a stratified ocean exactly?
Well, to me, actually, I've spent most of my professional life looking at rocks of what we call the Mesozoic era, which starts about 200 million years ago and ends with the end of the dinosaurs 65 million years ago. And one of the big surprises of what is turning out to be a fairly long life looking at these rocks is how rarely you find fossils. I mean, we find these rare places where there's so many fossils that it's so wonderful. But most rocks of that age turn out to be the results of this stratified ocean, where you're looking at sedimentary deposits in low oxygen conditions. We find lots of little pieces of pyrite, fool's gold, but we also see the rocks are layered. I mean, today when you have oxygen on a sea bottom, there are so many critters walking around eating, worms going through. They break up the strata. It's called bioturbation. But in the Mesozoic, there was so much warmth. There was so little current that these deep oceans, as Paul was talking about it, he's right, in the best of times, it's really hard to get oxygen down on the deep ocean. And in the warm times, it's almost impossible. And so we get these stratified layers, thin layers that indicate that there was almost no life on these bottoms. And that really seems to be what a world is like when you have very warm poles relative to the equator. I mean, why do we have any wind on the world today? Why do we have ocean currents? Because we have a heat differential. Heat migrates, you're right, heat migrates. And when you don't have a difference in heat between the poles and the equator, everything stops. We turn stagnant and we get these stratified oceans.
Well, you don't get such an organized global climate system, right? What happens is the temperature, the land is obviously warmer than the oceans, so that can create, you can get regional effects created where you get sea breezes and ocean and land breezes, and you get the monsoon type activity occurring, right? The monsoons are basically because of the temperature difference between the land and the ocean. So if in a world where the poles are much, much warmer, all right, that temperature difference to the equator is much, much smaller. So the overall organization of the wind and, the atmospheric movement circulation patterns and the ocean circulation patterns completely change, and you have more regional effects happening. Like, for example, we could think of monsoons happening in places where they would never really have happened before. I mean, some people in Norway have described to me how they're getting torrential rain near some of the coasts just because of that land-ocean contrast and very, very weak jet streams. And we know that because the jet streams are weakened and they're wavier and they get stuck in place, meteorologists call it a blocking situation, we can get heat waves in one place and torrential rains leading to floods in another place, and it can be persistent for long periods of time. You know, the areas under under the ridge of the jet stream are very hot and very dry, and when that condition persists, then we get all the wildfires and loss of many crops in those regions. So about 2/3 of the heat from the equator is transferred via the atmosphere and about 1/3 via the oceans, but we seldom talk about the slowing of the of the Gulf Stream and the slowing of the ocean current. But we're already seeing effects. I mentioned the global warming hole south of Greenland. Also, with the slowing Gulf Stream, it's overriding the continental shelf off the US more, and you're getting extremely warm water along these coasts quite often. And that's carrying into the fall. So now when we get colder temperatures, you know, over the land and very, very warm oceans off the US coast, we get these tremendous snowstorms along the East Coast in the fall, early winter situation. So everything changes when we're talking about these massive global changes of the rewiring of the oceans and the atmosphere. Everything is different, really, literally.
Okay, now I got a hint that the differential between the poles and the equator, the heat differential, is important because that stirs up it creates turbulence in the top layer of the ocean. Is that right? That's an important thing to keep it from stratifying too much. Is that relevant to the whole question of why the currents are slowing, if they are slowing? And I'm not sure whether you all agree that they are.
I don't think they are all slowing because we have to differentiate between the thermohaline circulation, which is a planetary circulation concerned with temperature and salinity, and wind-driven currents. I mean, people talk about the Gulf Stream as if it's part of all this, but in fact, it's a separate current system. It's driven by the wind. So we have to go. So the variations in the Gulf Stream depend on variations in the wind field in the ocean. But the thermohaline circulation is, in fact, a connected system. So you can, if you were Eric the Red and you threw an oar out of your longship in the year 1000 off Greenland, then in the year 2000, it would reappear off Greenland because it takes about 1,000 years for a complete circuit of the current in the thermohaline circulation. That's a very slow current system. But the point about it being slowing is it is true that the thermohaline circulation is slowing, and it's slowing primarily because of this failure of the chimneys to be produced. So there's a loss of the very vigorous vertical circulation in the North Atlantic, and the problem has been that happened in about 2005 to 2010, and the scientists who wanted to study this and what's happened now. I mean, basically, it's given that we're not getting chimneys taking water down into the deep ocean anymore. So where is convection happening, and how is it happening? And is it just a very much reduced type of circulation? But the trouble is, no scientists have been able to get any funds to go there. And I mean, not just myself, but French scientists, German scientists, all the people who've been working in the Greenland Sea on this convection process, that I think the funding bodies sort of thought, well, it stopped happening, so you don't need to study it anymore. And when it was, in fact, this is when we need to study it even more, because we want to know what's happened.
Well, do you have a theory about what makes it happen when it does happen? What creates the chimney, and when it stops happening, why?
Well, when we had chimneys, which we're able to follow them from their creation right through to the following summer, and it starts off in early winter in about November, and you've got a rapid growth of ice in the Greenland Sea, really rapid, because there's a part of the current, the East Greenland Current, diverts out into the middle of the Greenland Sea, so that you've got water which is cold but not frozen, moving out into the open sea, and ice growth happening incredibly fast. And it really happens fast because the air temperature is very cold, and there's a huge amount of turbulence in the water because this tongue of current is actually, it's called the Odden ice tongue. It's a tongue which is sticking out into the ocean with lots and lots of wave energy, and the wave energy is breaking the ice up into small fragments, causing it to grow faster. So you get a very fast growth of ice, and that the ice is rejecting salt all the time. And as it rejects the salt, that makes the surface water more dense, and that produces this intense convection underneath the ice tongue. And the trouble is that the ice tongue no longer grows there because of the warmer temperatures. So it's a complete change of processes that are going on in the North Atlantic. And we were able to follow and work out what the process was, but we're not able to see what the process now is because nobody can actually get any funds to go there. So that's a problem. But when you were still getting chimneys, I agree with that the predictions of climate models when you were having the Odden ice tongue was that it would actually give cooling or reduced warming in Northwest Europe or Western Europe, from Ireland down to France and Spain.
Let me interrupt briefly. You guys are living in the present day. Let's make all the ice go away. Now tell me what the global climate is then.
Okay, well, with the ice gone away, this won't happen anymore. So that was going to give you cooling in the Western Europe, and to compensate more intense warming in the tropical Atlantic, as they said that you're going to get more warmer surface water with probably more intense hurricanes. But
no, let me interrupt. Make all the ice go away. Come back with me to the Mesozoic. All the ice. We have no Greenland, we have no Antarctica. And it was a great comment about how we have monsoons are really a dominant weather process if we get rid of some of the thermohaline and surface currents. But the Mesozoic was a time of no ice. And we are losing, I'm not saying we're going to be out of ice within the next 2,000 years, 3,000 years, but at this rate, we will have no ice with this CO2 we're going to.
Well, I mean, the ice keeps the Arctic cool, of course. I mean, because the latent heat to melt the ice is huge, and the temperature is maintained at close to melting point above the surface. But as soon as you remove the sea ice, we're likely to lose sea ice very soon. 1 September, at the end of the melt season, and then, it'll freeze again in the winter, but not as thickly and not as extensively. And then perhaps within 3 years, there won't be ice, August, September, October. And then, within a few more years, July, August, September, October, November, and then basically an ice-free Arctic year round. And that's an Arctic that is much, much warmer because all of the heat will go into the warming of temperature. You're not getting a phase change. And so the oceans will become so warm in throughout the summer seasons that it will be very difficult for ice to form at all, I think, in the winter. But that's the controversial point. I mean, I think more and more people are coming to that viewpoint that we'll have ice-free Arctic year round. Then of course, Greenland's the only frozen spot in the Northern Hemisphere, and the melt rates, of course, will increase significantly over Greenland, and with the rise of sea level, and that will undermine the Antarctic ice shelves. I think, in the past, when sea level was much higher, Greenland is the most vulnerable place, I think. And then, but they're so connected, they're coupled, right? The ice in both continents. What's interesting with the Humboldt current, Paul Watson, is the Greenland, Antarctica right now has been incredibly cold. I mean, they've had temperature anomalies of like -4 degrees Celsius, as high as -4 degrees Celsius. It's actually quite fascinating. I mean, we've seen this sort of seesaw pattern in some of the paleo records, where when it gets very, very warm on Greenland, it's very cold in Antarctica, and vice versa. This seesaw pattern. And I think what's interesting is when less heat is going from the equator to the Northern Hemisphere, because the Arctic is warming by itself, albedo effects, et cetera, then more heat goes from the equator southward. It reaches about as far as Australia and forms this very sharp temperature contrast, very warm water north of Antarctica, and then very cold Antarctica. And that can almost isolate Antarctica, and lead to these negative temperature anomalies. And that's sort of you can see that sort of on a smaller effect with, as we've been rapidly losing sea ice in the Arctic, the sea ice in Antarctic actually was rising slowly, but that chain of event, that pattern in Antarctica was broken not too long ago, and the sea ice levels in Antarctica have also plummeted recently. So there's a lot of these effects going on, but I think it's really interesting to see. I don't know how much the Humboldt, the chimneys in Antarctica have been studied. I don't think they've been studied anywhere as near as much as in the Arctic. And my understanding was that the water descending in Antarctica in these chimneys was more widespread. It wasn't so localized as the chimneys are in the Arctic.
So please forgive me. Since I have actual data on your question, I figured I should at least show the map from NOAA, which relates to that. But I'm actually feeling very guilty, because I've been talking about one chapter in Peter Ward's book, the one about the mass extinction, the Permian Triassic, which was based on stuff like the Pacific, where things aren't.
This is right. This is the book Under a Green Sky, correct?
I've been talking about Peter's book, but this chart comes from NOAA data.
Right.
And obviously I have sources for that, but I don't want to bog everybody down with it.
Yeah, no, I've read Peter's book, Under a Green Sky, and I thought he was in good competition with Stephen King with that book.
Yeah. But
It's
the
a bit
point
of a
I want to
horror.
make is Peter has a chapter about the Great Permian Triassic event. And we should worry about a rerun of that kind of event, which would be based on the Humboldt current if I were to look ahead now. But before the Pacific is a problem, the North Atlantic and the Arctic, it's not as big a problem, but it's coming sooner. And the possibility of stratified ocean in the North Atlantic and the Arctic, it's another chapter in Peter's book. And Peter has another chapter on the partial mass extinction of life after the dinosaurs were gone. I think it's like Eocene. Peter can explain more. And having stratified ocean just in the Arctic and the North Atlantic, it was not enough to destroy all mammals on Earth, only the big ones. But since we are big ones, maybe we should pay attention to stratified ocean. If Britain
Paul, would
freezes
you
over, that
explain-
doesn't save us from Archaea.
Paul,
Stratified ocean is an issue, even if it's only the Arctic and North Atlantic.
okay, I love your map, but please tell me what it is, because I'm not used to looking at that map and I have no idea what it is. Explain it.
Okay. So what I ought to do is maybe in the chat, send you the citation.
I don't even know, I don't even know whether this is the Arctic or the Antarctic.
Oh, sorry, this is the Antarctic.
All right.
This is a map from NOAA, and you'll see it's a map of the deep ocean, the layers that carry the oxygen that power the Humboldt Current. Well, one side is the Pacific. That's the one that powers the Humboldt Current. And the problem,
I'm sorry, the north is the Pacific and the south is the Atlantic. Is that what you're saying? I mean, really, I can't orient myself at all
Okay.
to this map.
so to look, if you look at this map, you'll see Latin America to the left.
Oh,
South America, yeah.
Right. And the blue is good. The blue is thick water, a thick layer of oxygen bearing water. On the Atlantic side of the Antarctic, there's a lot of big, thick, deep water. On the Pacific side, there's a real problem with the thickness of the layers carrying the oxygen. The Humboldt Current goes along here. I don't know if you can see my cursor here.
Yeah.
But the most important pollineas or chimneys are right along here on this side of the Antarctic. They power the Humboldt Current. This is what carries oxygen to the Pacific Ocean. And you'll see that the current has been getting thinner, decreasing at about 114 per year. And you'll see the thickness is about, well, on this map, it looks like about 1,000 meters. The question is, when will the deep oxygen-bearing layers die because of these chimneys having problems? It's a big problem in the Pacific. But on the other side, way up beyond this map, near the Gulf Stream, it's a totally different story. But the different story looks like a stratified ocean coming sooner. This one, it looks to my eyeballs that we might be 30, 40 years from having a problem on the Pacific side. I don't know. What scares me is nobody knows. You were talking about money going to the people who could find out. We haven't had the kind of research we need to answer these questions. It's pretty scary when the best data we have is my eyeballs applied to just a few published maps from NOAA. We need better data. We need people to really figure out these numbers, but we need them for the Pacific and we need them for the Atlantic, both.
what do the numbers mean?
Okay, so minus 114 means you're losing 114 meters of deep Antarctic bottom water per year. And that's the oxygen carrying water, which brings oxygen to the Pacific Ocean and saves us from stratified ocean. If
It
this
brings the
dies,
oxygen, right, from the surface to the seafloor, and also carbon dioxide, which is very important because the ocean is a huge sink for carbon dioxide because it's brought down to the depth, right? So as the chimneys go, it's not just you get a deoxygenated ocean floor, you get less carbon being absorbed in the ocean. So the atmospheric levels will climb even that much faster, right? I mean, that's another factor that's very important.
the carbon dioxide cycle is very important in the modeling, but what worries me the most is the oxygen level.
Right.
Because you get low oxygen. We're not talking phytoplankton here. I love phytoplankton, these things that create oxygen for the earth at the surface. But in the deep ocean, there are these microbes called archaea, which want zero oxygen. You get rid of the oxygen, those things proliferate. Those are the ones that produce the poison that caused the mass extinction that Peter Ward has talked about.
Okay, now, as I understand it, there are two threats or two real dangers resulting from the change or the problems with this currents. One would be that Europe is going to freeze. And that's the first thing. And the second danger, which will take maybe longer, I don't know, is the production of excess hydrogen peroxide, hydrogen sulfide. For that is going to poison us all, right? Are those the two things we have to worry about? And what in the hell do we do about it?
You guys have reminded me it's not that simple, because even in the North Atlantic and Arctic, if Britain freezes over, that doesn't save you from stratified ocean. You can have a freezing Britain and a stratified ocean at the same time. And when you start to lose the Gulf Stream, you not only get freezing of Western Europe, you also get some ocean stratification. And locally, that could breed a little bit of poison. Maybe not enough to kill every mammal on Earth, but a little bit of poison can go a long way. And Peter's Peter knows more than I do about how poison in the North Atlantic can kill a few creatures.
Okay,
Well,
Peter,
the
tell
big-
us.
The big danger of all this is we don't know what's going to happen. I mean, nothing is certain. Secondly, yeah, thanks for the Stephen King. Maybe I should have got a Hugo Award for best science fiction. Sounds like your opinion is. The bad news is none of this happens fast enough to get response, governmental response. And we're talking hundreds of years, maybe thousands of years to really reduce ice enough to create major mass extinction conditions. None of this is going to happen next year. And therefore, there are so many other problems on this planet. I still think the greatest single problem facing us is a 2-meter sea level rise, which really will happen fast when you start flooding rice fields. If we can't feed ourselves, that is a major problem, coupled with the great heat events we're having. You're right. It scared the heck out of me seeing Seattle, Washington at 109 degrees Fahrenheit. That wakes you up.
Okay, take down this map. We've seen it enough.
Okay,
now. I
sorry,
wanna
I'm
look at
sorry.
pictures. Okay.
Okay.
All right. Now, so is it true that the two things that we're worried about have to do with the freezing of Europe because of this Gulf Stream and the longer term production of hydrogen sulfide? Those are the two greatest immediate dangers that we're talking about? And you want to talk about food, but we can't cover it all.
Well, I have a question for, I mean, those are basically problems, huge problems that we'll be facing very soon. I have sort of a question about the Carboniferous period, because this was a period when the poles were much warmer. We had forests growing in the Arctic. We had freshwater lake up in the Arctic. We had a much warmer world. And, you think of the vegetation with tropical forests and so on. So what
That was
happened?
the longest ice age in history. The Carboniferous was an entire glaciated period that lasted 30 million years.
Well, the period when I always thought that when vegetation was proliferating on the planet and the poles.
In the Devonian, we had this proliferation. By the Carboniferous, roots had gone so deep that they sucked so much CO2 out of it that we have glaciation that was the longest in the last 500 million years.
Okay, so the period when the Earth was much warmer, right, and the poles were warm, and there were trees growing up in the Arctic. Okay, we didn't have hydrogen sulfide release then that took out that caused a mass extinction, or did we? Like, did it develop over time and then end that period? Like, I'm not sure. I'm asking you.
Well, the best data for the hydrogen sulfide comes from biomarkers. So if we look at the end of the Permian and we start looking at the kerogens that are there, you get indications of green and purple sulfur bacteria. Isoreurotane is the most common, but also crocetane, which tells you that you've got a whole bunch of methanogens running around in the surface oceans. The purple and green sulfur bacteria can only live, as you know, with sunlight, but they also have to live in water that has no oxygen. So because of variations, this wasn't a global ocean covered with these green and purple. I mean, there's all, as you know, the land is going to be warm and the ocean's cold, so you're going to have variations. So at the end of the Permian, it's the concentrations of the biomarkers vary from place to place. But certainly the surface waters near land, many of them indicate huge amounts of hydrogen sulfide dissolved in the seawater at the surface, supporting these bacterial concentrations. And because of that, sea life, as we know it, the animals we love, were fewer and different. And so really we find this nastily at the end of the Triassic, at the end of the Permian. It didn't happen at the end of the Paleocene, but we certainly have a short-term global warming that appears to be, as I understand it, methane being released from high latitude. And it was nasty itself. So yeah, when we have these short-term, there are high times of hydrogen sulfide being released.
And I think more needs to be said.
Yeah.
The best single history of life on Earth now is a new book by Warden Kirschvink, which has a lot of current research, totally obsolescing the previous stuff. I have urged anybody interested in climate to read chapter 12 of this book by Ward and Kirschvink. And in that chapter, he talks about this great Permian extinction, but there were two elements required. One was the stratified ocean, but there was another element that was studied by a guy named Kump, and I hope we get to talk to Kump someday, because Peter talks about Kump in his book. Kump studied this great extinction, and the best evidence is you needed stratified ocean and you needed something like phosphate fertilizers in the ocean. And in the periods when we didn't have a fertilized ocean, there were times when there was lots of stratified ocean, but none of the H2S. That's well known. There were periods when there was lots of stratified ocean and no H2S problem. It turns out fertilized ocean was a critical marker, and that's important because we have a fertilized ocean today. That's what we humans have been doing.
Okay, what's the title of the book that you're referring to? You haven't said the title.
Ward and Kirschvink. I look it up by the authors.
Yeah, those are the authors, but what's the name of the book? I mean,
It's called A New History of Life, 2015.
A New History of Life. Okay.
Mm.
Well,
Okay, now
maybe
this
I could-
again focuses my mind on the question of these fertilizers, or these, if the phosphates or the nitrates being washed off the land into the ocean, or deliberately put something equivalent. What Paul wants to do is sprinkle iron filings in the ocean, which would have the same effect, increasing algae and increasing phytoplankton. Is this good or bad? It looks like Paul has told me, or I believe, that would be great because it's going to suck the carbon dioxide out of the atmosphere and take it to the bottom of the ocean and
In the short term.
sequester it.
Yeah,
In the
maybe
short-
it
okay.
kills the world in
Now,
the long term.
this is what I want to get straightened out. But Peter Ward then scared me about what Paul just said. Paul Werbos just said that these phosphates and things are going to create the same effect, but when it gets to the bottom, it's going to take all the oxygen out and allow these microbes to proliferate and produce the sulfides. So which way is it? Should we be sprinkling things in the ocean, or should we make a big effort to stop doing anything like that?
Well, I think it worked with the iron filing method, and in fact it works too well because it produced effects that were very large and measurable, and upset the Canadian government when it was done in Canadian waters. So that works. But I'd just like to pick up on something that Peter said. When we're talking about all of the changes that are going on with ice disappearing and with changes in the water structure, we are talking about, on the whole, hundreds of years or long periods. But if we're looking at sea level rise, we're looking at now, and we're looking at, and the sea level rise is something which is inexorable. All of these other changes we can, in theory, do something about if given time, but sea level rise we can't. So there's nothing we can do about it, and can easily get 2 meters, and some scientists say 4 meters by the end of the century. In fact, somebody I really think is one of the greatest ice scientists, that was Connie Stephan, was saying we were going to get at least 4 meters of sea level rise by the end of the century.
Please let that not be true. That scares the heck out of me.
Yeah,
2 meters is disaster. 4 meters is catastrophe.
Catastrophic. Yeah, and he really knows. He spent his whole life on this, and then he got died in falling down a crevasse. So that quantity, that amount of sea level rise, considering it's worldwide, and it applies to cities, towns, rural areas, places where people are trying to grow crops, and it just as you mentioned, the growth of rice cultivation, for instance, is affected by that. So something that's going to affect us far more than anything else is in terms of what the ocean's doing, is sea level rise, and it's looking as if it's accelerating rapidly, and we simply can't do anything about it. So that's what we should be worried about.
So one of the things that comes out of this is we need more critical research. We even the best opinions of the best knowledgeable people are not certain. And I've just learned that because I was actually surprised you guys thought it would take so long. What I have proposed is that in the research to understand the problem, we need to have an effort to understand precisely what are the conditions when these bad archaea producing H2S proliferate. I had the impression that if you have the right conditions, archaea microbes proliferate overnight. It's like a tipping point. When the conditions are right for these guys to go nuts, they can go nuts very quickly. That's my impression. But we should have research. I've even imagined aquarium level research. There are cases of kids who generated these conditions and their whole neighborhood got blew out. There are press stories where kids didn't know what the hell happened. You had low oxygen, you had the right conditions. It's not that hard to generate the conditions where these bad bugs proliferate fast. So the question is, we need to know exactly what kind of chemical and oxygen conditions lead to the rapid proliferation. My guess is that when you cross the threshold, you are immediately in deep shit when you weren't the day before. But on the other hand, we need to do research. We need aquarium level research that universities could do to better understand exactly what are the conditions where these H2S archaea proliferate.
Okay, is my job to invite Mr. Kump? Maybe that's the next conversation. Is there anybody who knows anything more than we have covered in this conversation? Peter Ward, you would know who knows the most. Do you? Peter Ward?
Oh, I thought you were talking to a different Peter.
No.
Lee Kump is a great friend and a great scientist. I think he'd be fantastic. He's very good at explaining this stuff, and he has been working in lakes in New York. I mean, Paul, you're talking about aquaria. There's lots of natural aquaria. Lots of freshwater lakes turn into these little aquaria producing the hydrogen sulfide, just as those beautiful jellyfish lakes in Palau do the same sort of thing. I've been very impressed by the ability of aquatic biologists to really look into the chemistry of these places, how it scales up to a global sense. I mean, I don't think we're going to be anywhere in the next 10,000 years needing gas masks for hydrogen sulfide into the atmosphere, at least I hope not. But then again, Kump modeled how when chemocline rises, how much H2S does rise into the atmosphere. And his initial work suggested that the biggest danger was that it breaks down ozone layers. And when ozone is run or disappearing, then you get so much radiation, solar radiation, that affects plants. But maybe we should have Lee come on and explain it in his own words.
Well, let me see if I can get him.
Yeah.
Now, which of you guys want to come back and talk to Kump?
I always can learn. Whenever I hear Kump talk, I learn something new.
Anybody else want on this project next
Sure,
go
sure,
around?
I'd be very interested.
Okay, all right. Anybody else?
One of the things I just want to mention, I think a few years ago, I heard there was of hydrogen sulfide coming up from the ocean, off South America, the west coast of South America, affecting some animals on the land along the coastline. There's anecdotal stories and it's a very deadly gas and in very low concentrations. There was a story about a jogger running along a river who just dropped dead. And, apparently they investigated and there was some hydrogen sulfide being produced in that region. I don't remember, what the source was, but, it's also, I think, hasn't it been a problem in mines in the past? you know, a little bit of hydrogen sulfide, and you know, all the miners drop dead. Like it's
Well,
it's a very incredibly toxic.
There's a lake in
have
Africa
covered
where
out here in the Pacific Northwest, the old logging camps. So now a lot of these old logging camps and railroad ties buried for 200 years have had enough time in zero oxygen to be producing pockets of H2S. So the groundwater people in the Seattle area and all around here now are now required to have an H2S meter when they start drilling, because there are pockets emerging of hydrogen sulfide coming up from just old logging waste, which we have everywhere around here, of course.
Mm.
So, but again, that's quite localized, and wind
Yeah.
blows it away. But the fact that we can detect such low levels with our nose, I mean, if you go into a Mexican restaurant after somebody's had a lot of beans, you can detect that hydrogen. You get some of that because we know it's dangerous.
Yeah, exactly.
Okay, well, our time is up and then some. So my next assignment is to try to get Lee Cope to come back and join you guys, or some of you, anyway, some combination. I'll get back to you. Okay,
Meta,
So
thank
thank
you
you.
so much.
thank you very, very much. This has been fascinating and extremely important.
Can I ask one
Okay.
quick question of Peter? Are you working on another book, Peter Ward?
yes, I'm working on one called Mining the Sky. It's about direct air capture.
Okay,
Well,
you are. How about you, Peter Ward?
I published a book last week on sea level rise. The Americans wouldn't publish it. It's only in German.
Oh,
Oh my God.
okay.
The Germans
Okay.
don't, but the Americans said, no, there's no interest here in sea level rise.
Yeah, I feel I need to write a book, you know, to
Well,
be,
let's,
be invited on to Meta's next program.
Indeed.
hey,
Bless
talk
you.
to me. Talk to me. I got an agent. I'll do one with you. I'd love to write with you. I mean, you know way more than I do about this stuff. And maybe a paleo concern with a modern day look is the way to go.
Yeah,
I'm serious.
could
All
be a
right.
good idea.
There we go. I'll talk to you
All
guys.
right. We've got a
Okay.
book organized already. That's pretty
Okay.
productive.